Hello, I'm here to talk about the science and mathematics of eclipses. This is a talk that I gave very recently at Camp Ondesonk, Illinois, where we went to see the complete solar eclipse on April 8th. After the talk, several people came to me and said it's very good and they would like to have a recording of this so that they can share with other people. So I'm making this talk available on my YouTube for those who want to watch it again, or for those who couldn't watch it when I gave it at Camp Ondesonk. There are three parts to this talk. The first one is about basic questions on solar eclipses. And the second one is eclipses and astrometry, which is a branch of astronomy which deals with positions, velocities, and distances in the universe. And the final part talks about the role of eclipses in our understanding of gravity. I'm going to take a mathematical perspective on these three topics. I will tell you interesting stories, and hopefully you will be able to connect with what I'm about to tell you. So let's begin. Basic questions on solar eclipses. First, what is a solar eclipse? I'm sure you all know this, but to set the stage, I would like to define a solar eclipse for you. So here is a simple anatomy of a solar eclipse, a plain vanilla version. And a disclaimer is that throughout the talks, the pictures that you're going to see are not drawn to scale. So here's your sun and moon going around the Earth in its orbit. And you can imagine occasionally the shadow of the moon is going to fall on Earth. And if you happen to be within that shadow, you get to see a solar eclipse. So the solar eclipse occurs when the moon comes in between the sun and the Earth. Okay, but obviously there's a lot more going on there, but that's the main idea. And if the moon is on the other side, and if the shadow of the Earth falls on the moon, or if the moon enters the shadow of the Earth, then you get a lunar eclipse. So today we'll be focusing mostly with solar eclipse, although I will be talking about lunar eclipse in a few places. Okay, if that is all there is to it, then why don't we see a solar eclipse every month? A very natural question that begs to be answered. And the reason you don't see a solar eclipse every month is because the orbit of the moon's orbital plane is tilted by about 5 degrees with respect to the orbital plane of the Earth going around the sun. So that's called the ecliptic. Because these two planes don't line up, you don't get an eclipse every month. And here, the geometry will help understand what's going on. If you look at this picture on the right-hand side, even though the moon is in between the sun and the Earth, the shadow of the moon does not fall on the Earth because the moon is above the ecliptic. Similarly, if you look at the picture on the left-hand side, the shadow of the moon is below Earth. So not only the moon must be in between the sun and the Earth, but it should also be on the plane, the ecliptic. Only then you can get an eclipse. So in other words, the line segment joining the center of the sun, the center of the Earth, the center of the moon, they should all line up. All these centers should be collinear. That's when you cast an eclipse. So therefore, you get what's called an eclipse season, which happens about twice a year. And only during that time, you can hope to see a solar eclipse. Otherwise, you can't. And you hear different types of eclipses. What causes that? And that is due to the eccentricity in the orbit of moon going around the Earth. The moon does not go around the Earth in a perfect circular orbit with Earth at the center. It goes in an elliptical orbit, and at the shortest distance, which is perigee, it is 225,000 miles. And at its longest distance, which is apogee, it is about 250,000 miles. The difference of about 25,000 miles is responsible for the different kinds of eclipses that we see. And typically, there are three types of eclipses. One is total eclipse, when the moon is right at a place in between sun and earth for people who are in the umbral region to see a complete eclipse. So this darkest shadow of the moon, that is called the umbral region, and outside it will be the penumbral region. But if the earth is much farther away from this point, let's call this the focal point where these tangents meet, then you get an annular region, annular eclipse. So if you're in this region in the umbral part of the shadow, from your perspective, the moon does not completely cover the solar disk. It leaves out a little annular region that will be visible. So that's why you get an annular eclipse. But if you are anywhere else in the penumbral region, then you get to see a partial eclipse. Okay. There is yet a fourth kind of eclipse called a hybrid eclipse, which is very rare. And that is, you can be inside the path of totality, but at different points within the path of the eclipse, you get different eclipses because the curvature of the Earth is just enough for you to move from a total to a partial or an annular eclipse, right? Again, the timing and position must be just right for that to happen. It's a very, very rare case. But these are the three types of eclipses. The one that happened on April 8th here in Illinois that we went to see was a total eclipse. There is also something called the magnitude of an eclipse. Every solar eclipse has a number associated with it, which tells you basically the fraction of the sun that was eclipsed. So the official definition is that the magnitude is defined to be the ratio of the apparent size of the moon, the surface area of the apparent size of the moon divided by the apparent size of the sun. That ratio is the magnitude. So if you have a perfect eclipse, the magnitude should be equal to 1. So you're going to be right here. So when the lunar disk perfectly covers the solar disk on the sky. But if the Earth is closer, and if you're in the umbral region in this part, okay, then what's going to happen is that the moon covers a bit too much, and you get a magnitude greater than 1. So, but if you're further in this green region, then the moon doesn't completely cover. You get an annular eclipse where the fraction covered is less than 1. How can we predict an eclipse? And this is a very, very difficult question and very important question. Okay, and people have studied eclipses, and they kept records of eclipses for a very long time. I mean, all the ancient civilizations, the Indians, the Chinese, the Babylonians, they all were keeping track of eclipses because they were fascinated by it. And as a result, these serve as anchor points in history. So if you know an event in history happened in a window of time that you are not sure, but you know that it happened not too far after a solar eclipse, then you can actually more or less pin down when that event happened. So they serve as beautiful anchor points. The reason the prediction problem is hard is because of the complexity of the motion of the moon. Normally, when we talk about the lunar month, we say it's like 29, 30 days, we round it off. But there are three different types of moon months. One is the synodic month, the time from a new moon to new moon, which is 29.5 days. Anomalistic month, time from the shortest point in its orbit back to the shortest point to the distance to the Earth. So that is perigee to perigee. And the draconic month, which is going from the node to the node. So I guess I didn't explain node. A node is the point where the orbit of the moon cuts the orbit of the Earth. So as it goes around the Earth, so there'll be one point where it's going to come from below and goes above. That is the ascending node. And then it goes from above to below. That's called the descending node. So in ancient Hindu astronomy, these are called the Rahu and Ketu. Now, all these three cycles, when they line up at a time that will be the least common multiple of these three time periods, which is roughly 18 years, 11 days, and 8 hours. So that length is called a Saros cycle. Now, if you look at the distribution of solar eclipses, the time distribution, okay, that looks like a messy data, but if you separate them into different families, which are separated by this time period, an interesting pattern starts to emerge. And that's the pattern people use in predicting eclipses. So all these Saros cycles are classified. So you have even numbered and odd numbered Saros cycles. So depending whether the moon is at the ascending or descending node during the eclipse, right? So here is one cycle, Saro 136. So if you look at the pattern here, so this is the path of totality in 1937, which is going below the American continent. And then the same cycle, the same eclipse was visited again 18 years later in 1955, which is going above Australia, Pacific Ocean. And then another 18 years later, you have it going along the African continental plate. So that is the Saros cycle. And you also see that it is not at the same place. The path looks very similar, but it's not at the same place because of the 8 hours. So 8 hours is 1/3 of 24. So that is 1/3 of 360, which is 120-degree rotation. And that is why these eclipses in this cycle are shifted westwards 120 degrees. So here is Saros cycle 139, which is the one that happened on April 8th. As you can see, these cycles, the odd numbered ones at least, they start from the North Pole and they march towards the South Pole, and the even numbered ones, they do other way around. So these Saros cycles are very important. They can help to predict when the next eclipse is going to be. So that's the first part, talking about basics of eclipses. Now let's move on to eclipses and astrometry, which is the science of measuring distances, positions, and velocity in the universe. Let me start with a very basic question, and that is, what is a proof that the Earth is round? We all know that the Earth is round. but what is the proof? There are many proofs out there, but the first and perhaps the most elegant and compelling proof is coming from eclipses. And this time it's a lunar eclipse. And this goes back to Aristotle, who first observed that that during a lunar eclipse, when the moon enters the shadow of the Earth, the shadow it casts on the moon is always a circular arc. And then he observed this many times, and then he drew the following remarkable conclusion that if you are a shape that is always casting a circular arc, you must be a sphere, because there is only one shape that does that. If you take any other geometric shape in some orientation, you will cast a non-circular arc. And he noted that every time, this doesn't matter in what zodiac the sun is, in what phase the moon is, it's always casting circular arcs during a lunar eclipse. So that is a elegant indirect proof that the Earth is round. Okay, next question. How big is the moon? And here is another interesting calculation making use of the timing of a lunar eclipse. And this one was done by another Greek astronomer, Aristarchus. So he said, I'm going to time the lunar eclipse. So he saw how much time it took for the moon to enter the umbral region, right? And he estimated using the timekeeping devices at the time, it could be water clocks or sundials, whatever, to be 50 minutes. And then he said, okay, then I'm going to see how much time it takes after it entered the umbral shadow. He said, I'm going to see how much it will take for it to cross the umbral region, and he estimated that to be 200 minutes. Yeah. And then he said, there is no reason for the moon to speed up or slow down in its orbit, so it's moving at a uniform speed. Therefore, the time it takes to sweep its own diameter must be proportional to its own size, and the time it takes to sweep the Earth's diameter is proportional to the Earth's diameter. So using simple theory of proportions, he was able to calibrate the ratio of the diameters of the Earth to moon as 200:50, which is 4:1 ratio. Simple, but quite incredible. So to put it differently, the moon is about 25% of the size of the Earth, 1/4, right? And by modern standards, that's pretty accurate, because the moon is about 27% the size of the Earth. And using just simple experiment, Aristarchus got 25%, which I think is quite incredible. Next, how big is the sun? This time, we need a solar eclipse. What I'm about to show you here is one of the most incredible coincidences in astronomy. When you look at the sun and the moon in the sky, they both appear to be about the same size. Their apparent sizes are more or less the same. But in reality, we know that the sun is much farther away and it's much bigger away. But the numbers work out just right. And this can be seen remarkably during a total solar eclipse. The sun is much farther away. It's 400 times farther away, but it's also exactly 400 times bigger. And this perfect ratio is the reason why we get to see total solar eclipses. So in geometrical terms, you have two triangles, a big triangle with the diameter of the sun as the base, and a small triangle with the diameter of the moon as the base. And these two triangles are similar. And you know that when triangles are similar, the ratio of corresponding sides is the same. Excuse me. So the diameter of the sun to the diameter of the moon is in the same ratio as the distance to the sun over the distance to the moon. And again, Aristarchus was able to measure this distance just by holding a little coin at arm's length to cover the lunar disk and measuring the length of his arm and the length of the coin, and he got about 400, right? So quite an ingenious stroke of brilliance, right? And once you know the diameter of the moon from the previous slide, you can multiply with the diameter with 400 to get the diameter of the sun. Okay, this time it's not as accurate as last time, but in principle, they were on the right track. So this shows the power of a simple Euclidean geometry in astronomy. So that's the point. Okay, how big is our Earth? It turns out this is the most difficult question. So the earlier two computations I have shown you, the size of the Earth, size of the moon and size of the sun were all in relation to the size of the Earth. So if you want absolute numbers and not relative measurements, you better figure out the size of the Earth. And that is a very challenging problem. How are you going to measure the size of the Earth on which you're standing? You can't see it all. And because of the curvature, you can only see a limited portion of the Earth. How are you going to measure the curvature and from there the size of the Earth? And this is probably one of the most remarkable stories in geometry. And it was done by Eratosthenes, who was the chief librarian of the Great Library of Alexandria during that time period, 276 to 195 BC. Around that time period, he was the chief librarian. And Alexandria was the intellectual hub of the ancient world. You know, people from all around the world would go to Alexandria to study. So there would be lots of scholars, books, discussions. So it was the hub. And at Alexandria, on one fine day, Eratosthenes was reading through some old manuscript, and then there he read something very curious, and that on June 22nd, or whenever summer solstice was around that time, in the city of Syene, right at noon, vertical sticks to the ground cast no shadows at all. And the reflection of the sun at that time could be seen at the bottom of the wells, right? And he thought that was very intriguing observation. And he said, okay, I'm going to wait for summer solstice and do an experiment to see if sticks really cast a shadow. And he was living in Alexandria, which is north of Syene. And on summer solstice, he did the experiment. So he went out and yes, vertical sticks were casting definite shadow. And then he asked, how could it be at the same time a stick back in Syene, a vertical stick to the ground back in Syene would cast no shadow, but a stick in Alexandria would cast a definite shadow? And it was clear to him that the only reason this is happening is because of the curvature of the Earth. And bigger the curvature, bigger the difference. So what he did, he measured the angle in which the sun rays were falling relative to the vertical stick on a ground. He was able to measure that very easily by measuring the length of the stick and the length of the shadow and simple trigonometry. He was able to get the angle. And now if you extend these two sticks, imaginary sticks, all the way down to the center of the Earth, they should meet at the same angle. And that was about, 6 or 7 degrees or something. Because, these will be alternate interior angles, which are congruent. So that is the number. So now, in order to find the total circumference of the Earth, all he needed was the distance between these two cities, Alexandria and Syene. Now, the story goes that he hired a man to pace out the entire distance between the two cities. So he would hire this man to pace out the entire distance, and he knows roughly at what speed this man was walking. And talking to him, he found out how many days it took him, how many hours he was walking each day, and he came up with a rough estimate. So if 6 degrees corresponded to that distance, how much would be 360 degrees correspond to? A simple proportion gave him an estimate for the full circumference of the Earth. And once again, here, due to his ingenuity and a stroke of luck, he got a pretty accurate answer, okay, with an error of only a few percent. What is the distance to the moon? And this was done by Hipparchus, one of the later Greeks. Another incredible story. This is during a total solar eclipse. Okay. So Hipparchus observed a total solar eclipse from the place where he was living, and then he heard that his friend, who's few 100 miles south, only got to see a partial solar eclipse. Okay, and then again he became very curious. How could it be that at the same time I'm able to see a total eclipse and my friend down south is seeing a partial eclipse? He was very good with geometry. He actually developed trigonometry trigonometric tools for measuring distances and so on. So he was able to quickly draw some pictures and do some simple calculation to figure it out. So they knew their local latitudes by measuring the angle of elevation to Polaris, so theta and phi, and then the difference between those two latitudes they were able to compute, and they knew the radius of the Earth. So that will give them this region, the length of this arc of the Earth's great circle connecting their two hometowns, right? Now his friend was able to see only a partial eclipse, only 1/5 of the eclipse. So only this bottom part. So if you take the sun, 1, 2, 3, 4, 5, you cut it into 5 equal parts. His friend from down below was able to see only the bottom 1/5 of the sun. And then again, using clever trigonometry, he was able to figure out the distance to the moon. And that's the work of Hipparchus. Okay, that's the end of the second part of the talk. I hope now you understand how eclipses helped in astrometry, measuring distances to sun, moon, and measuring their true sizes. Now moving to the final part of the talk, which is eclipses and gravity. I want to say a few words with the Newtonian theory of gravity. So what is the Newtonian theory of gravity? It is probably the first universal law in science. It states that any two objects in the universe with masses, let's say m1 and m2, attract each other with a force that's directly proportional to the product of the two masses, m1 times m2, and inversely proportional to the square of their distance. And the constant of proportionality is this famous gravitational constant G. So this was done by Newton, and it's a long story how he arrived at that. So that will be a topic for another talk. Starts off with work of Galileo, Kepler, and trying to understand their work. So he tried to figure out the nature of the force that's responsible for elliptical orbits, and then during using calculus that he built, that he invented, he was able to come up with this grand inverse square law. I just want to share this favorite picture of mine. that I took in Trinity College in my visit to Cambridge last summer. So this is in Trinity Hall in the chapel. So that's the statue of Newton. Now, that is just a theory. But how do you know if it's true or false? For that, we need some confirmation. So every good scientific theory should come up with some predictions that are verifiable. And Newtonian theory of gravity predicted a solar eclipse, and this prediction was done by a friend of Isaac Newton, which is Edmund Halley, so after whom the comet was named. And actually, Edmund Halley helped also in the publication of Newton's Principia, this masterpiece. Newton was painfully slow in publishing, and Edmund Halley really knew the impact this scientific work would result if it was made available to the scientific community. So he went out of his way, even using his own money to help in the publication of Principia. So he really believed in the Newtonian theory of gravity, and he did the math to figure out the next eclipse that's going to hit England. So he made this audacious announcement that a solar eclipse would hit London at 9:05 a.m. on May 3rd, 1750. It's a pretty bold and precise prediction, right? So you can tell that he actually did the math, and you can't just pull out of nowhere, right? So people waited for this auspicious moment, and lo and behold, exactly as predicted, on May 3rd, 1715, at 9 o'clock in the morning, the city of London, the sky turned dark. So this was a dramatic confirmation of Newtonian theory of gravity. And to really appreciate the work, you have to understand that in 1715, there were no computers, no calculators, nothing. Even logarithms were not developed there. So he had to do all the math and all the hard calculations by hand. So quite a ingenious feat, if you ask me. So that gave a confirmation of Newtonian theory. But there is more to it. This is not just the only thing, because, oh, by the way, before I go to the next one, I just want to show you the picture of the nights of the sky during the eclipse of 1715 in London, simulated using Sky Safari. So the Newtonian theory of gravity also helped in the discovery of Neptune. It was the first planet to be discovered after it was predicted mathematically. The remaining planets were just observed with naked eye or a telescope, right? But Neptune was a different story. It was mathematically predicted. The existence was predicted by mathematics, and later people found it using telescopes. So let's see how. So for that, I need to back up a little bit and start with William Herschel and his discovery of Uranus, right? So William Herschel is one of the greatest observational astronomers, and he observed lots of things in the night sky, clusters, comets of planets, moons of planets, and so on. And here is a replica of a self-built telescope. So William Herschel and his sister Carolyn worked together jointly on a number of projects. So the story goes that on 13th March 1781, it was a fine day, so the Herschels, they had their dinner and they said, okay, let's go out and do an observation. So that's what they would do on a clear night sky. They would just go out and observe. And Herschel noted a new object in the constellation of Gemini using a telescope that he built himself, that I showed in the previous slide, right? He observed a new object, and Herschel knew the night sky in and out, right? So he found a new object. He thought it was a new object, and he went back and looked up his own records of his drawings of Gemini constellation. It's like, this was not there before. Where does this pop up out of nowhere? Okay. So then he recorded on 13th March 1781 in the quartile near Zeta Tauri, either a nebulous star or perhaps a comet. So back in those days, everything that's not a point light is a nebulous star, some nebulosity, with some nebulosity, or a comet, right? He was not sure. Okay. So what I'm about to show you is an interesting way of arriving at the conclusion by elimination and deductive reasoning. Okay. So he eliminated that it was a comet because it changed its place. So in just a matter of few days, from 13th to 17th, in a matter of 4 days, the comet changes a place, right? And stars, nebulous stars, don't change positions so rapidly, right? So he ruled out the possibility that this could be a comet. And upon closer inspection, it didn't have a comma or a tail, and its orbit is almost circular, right? And it is known that comets have tails, and also they have orbits which have much higher eccentricity, right? So that's certainly gone. And then Feb 7th, 1782, it now appears that this is probably a primary planet of our solar system, right? So once again, he eliminated that it's a star because it changed its place, right? And then stars don't change place so quickly. And then he eliminated that it's a comet because of its circular orbit. It's almost circular orbit, so it's not a comet. So now it appears that it's probably a primary planet of our solar system. Oh, this exclamation is due to me, right? I got very excited. It's a beautiful logical deduction, right? And maybe at this point I can also quote what's his name, Sherlock Holmes. When you have eliminated the impossibility, whatever remains, however improbable it might be, must be the truth. So he eliminated the possibility that it's a comet or a nebulous star. So there's only one thing on the table, so it must be a primary planet. So serendipity, incredibly remarkable. He had no plan of discovering a new planet. It was just a casual observation of the night sky, and he found a new planet. And what's even more fascinating here is that through his casual observation, he almost doubled the size of our solar system. And this planet, which was accidentally discovered, was later named Uranus, in the honor of the Greek god of the sky. And once again, here is Sky Safari showing us the night sky of London on March 13, 1781, around 11:30 p.m. So there is your planet, Uranus. Okay, so that was Uranus. And how was Neptune discovered? So Uranus was discovered and people got very excited. They were observing it and tracking its orbit. And as they got more and more data, people started seeing some anomaly here. So it was not following the orbit that was predicted by the Newtonian theory of gravity. So it was going a bit off track. And that raised some questions. Why is it going off track while the remaining planets are obediently following the Newtonian theory of gravity? Why is this guy behaving in such a funny way, right? And people came up with different explanations. One was that maybe Newtonian theory does not work at such long distances. This sometimes happens in physics. Um, physical laws apply within certain range. Okay, so if you're too close or too far, I mean, that is like extreme scenario. Then things might break down. But others were not convinced. They said, that doesn't sound right. What's plausible is that there is maybe another planet further out, which is hugging Uranus. Maybe that's what's going on. Okay, if that's the case, then where is it? So the mathematicians got excited. They rolled their sleeves and started doing all the math. And two mathematicians were successful in completing that calculation. One is Urbain Le Verrier in Paris, and the other one is John Couch Adams in Cambridge, more or less simultaneously, independently, in 1845, did the math, and they were able to pinpoint where this fictitious planet must be based on the observations they had of the planet Uranus. So the story goes that Urbain Le Verrier sent his work to, I think, Berlin Observatory, and John Couch Adams sent it to the Greenwich Observatory. And then this person who received that in Greenwich said, "Oh, this is some mathematician telling me where to look for a new planet. This is nonsense." He just threw it in the dustbin. But Le Verrier sent it to Johann Galle, who's at Berlin Observatory, and he was like, this is interesting. If I turn my telescope by this degrees in right ascension and this degree in declination, I'm going to see a new planet. Very interesting. Let me try it out. So he tried it on September 23rd, 1846, along with his assistant at Berlin Observatory. They tried it, and within just 15-20 minutes, they actually found a new planet. So this is an incredible story which shows the power of the Newtonian theory of gravity. The mathematical equations predicted this new planet based on the anomaly of the orbit of Uranus. And once they predicted, it became very easy to hunt it down. Otherwise, the night sky is too big. So where are you going to look for? So math is like a torchlight. It tells you where to look, right? And once you narrow it down, then you can turn your telescopes in that patch of the night sky, and you can hunt it down. And that's exactly what happened with the discovery of Neptune. And once again, here is Sky Safari's simulation of September 23rd, 1846, Berlin night sky. And there you can see the planet Neptune shining brightly. Great. Newtonian theory is excellent, but it's still not perfect. It's not the full story. So it was able to explain, it was able to predict a new planet. It was able to predict a total solar eclipse, and that's great. But there are some things it was not able to explain. And one of them is the orbit of Mercury, which precesses as it goes around the sun. And the Newtonian theory gives you a number for the precession rate, but what's observed is something different. Things were not adding up. What's observed is 5,600 seconds of arc per century, but what Newtonian theory gave is 5,557 seconds of arc per century. So that is a pretty small difference between what's observed and what's being predicted, but this difference adds up over time, and the difference is quite noticeable. And then people said, okay, maybe there is a planet, and they hypothesized that planet is Vulcan. Just like Uranus orbit was nudged by planet, outer planet Neptune. Maybe similar thing is going on with Mercury. Maybe there is a inner planet which is too close to the sun and we can't see it. It's lost in the glare, which is influencing Mercury. But I mean, Mercury is already very hard to see because it's so close to the sun. How can you see a planet that's even closer to the sun? The only hope is to see it during a total eclipse. So people waited for a total eclipse of the sun. Every eclipse they observed it, but they couldn't. The planet was not just there. So then they had to scratch that thing out. So there is no such planet which is influencing Mercury. So that's too bad. So what else can we do then? So that's when Albert Einstein enters the story. So in 1915, about 10 years after he published the special theory of relativity, Einstein proposed the general theory of relativity, where he was able to explain gravity. The special theory did not have gravity, right? But 1915 general theory of relativity has gravity in it, and he was able to formulate a new theory of gravity. And he said, we can get rid of Newtonian theory of force. There is no such thing as force. He said simply the distribution of mass and energy in the universe, or what he called the space-time fabric, causes curvature, and objects move along geodesics, the shortest paths in this curvature. So imagine a big star like the sun, because it's so heavy, it's going to distort the space-time fabric, causing these bumps, and objects like planets, they actually move along the geodesics, the shortest paths caused by the deformation of the geometry, the local geometry around that star. So that's the idea of the general theory of relativity, and it can be formulated very precisely using mathematical equations and so on. And Einstein's theory of relativity predicted that things going to be deformed, even light rays will be bent as they pass nearby stars. And if you look at this path of light, as it is going close to the star, it's actually its trajectory is diverted, right? So that's the deformation of the light. And the theory predicted to what degree, what angle the light ray will be bent as it passes close to a big star like a sun. The sun's gravity bends light rays, right? So here is a better picture. So light coming from a distant star A gets closer to, as it gets closer to the sun, it bends and it reaches the Earth. So from our perspective, it appears as though the star is here, when in reality it's over there. This shift, the predicted angular deflection is 1.75 arc seconds. Okay, then we have to observe that. And for that, again, we have to wait for an eclipse, because if you want to do any observation of anything close to the sun, you have to wait for a total eclipse when the moon is going to block the sun, and then you can see what's going on in the background. So you can measure the stars on a different night, and then again, when the sun is blocked during the daytime, and you can see and you can photograph those stars, and you can measure the two photographs, and then you can see how much distortion happened. And people waited for the eclipse of 1919, that was the best time to make this observation. So things were delayed during World War I. So after the war, on May 29th, 1919, people waited for the total eclipse to do this experiment. So here is a picture of the total eclipse on May 29, 1919. As you can see, the sun is in front of a bright star cluster, bright collection of stars in the constellation of Hyades. So that was very good, because in order to do this experiment, you need to take photograph of stars. They better be bright enough so that you can capture on your plates. And once again, you observe these stars first in the night sky, maybe the night before or something, and then you wait for the eclipse, and again take the photograph when the sun will be blocked, and then you measure the two plates. And this experiment was conducted by this British astronomer Arthur Eddington. So he was leading this project, and there were two teams, one from the Cambridge Observatory, another one from the Greenwich Observatory. One went to Brazil, the other one to West Africa. So here is a picture of the instruments they were using in Brazil in 1919. And they got the data, and here are the results. So this is the radial shift of the various stars at various distances. And as you can see, the data obtained lines up very closely with Einstein's theory of relativity, and not the Newton's theory of relativity, Newton's theory of gravity. Okay, so Einstein's theory of gravity is a far superior model that explains gravity, that supersedes the Newtonian theory of gravity. Although for most terrestrial things, you don't need Einstein's theory, but if you want really accurate answers, like GPS and other things, you want Einstein's theory. And that is why the eclipse of 1919 is regarded as the most important solar eclipse in history, because it completely changed our perspective of the universe. The two most important pillars of modern physics are general theory of relativity and quantum mechanics. And general theory of relativity was proposed by Albert Einstein, and the total eclipse of 1919 was the first confirmation of Einstein's theory of general theory of relativity. And since then, it has been experimentally verified hundreds and hundreds of times in various precise experiments worldwide. And when this experiment was conducted, and it confirmed Einstein's theory of relativity, Einstein said it in a humorous way: "The problem conceived by my brain was solved by the bright Brazilian sky." Okay, that's the end. Now let's summarize what we learned in this presentation. Number one, eclipses helped kickstart astronomy. And right from the beginning, lunar eclipses revealed the size of the moon. Solar eclipses revealed the distance to the moon and the size of the sun, right? The famous experiments that I talked about, Aristarchus and Hipparchus and other people, right? And these were just a few rungs of the cosmic distance ladder. The cosmic distance ladder is a sequence of computations that you do, which build on the top of one another, okay? Going to the higher rungs. The first few rungs, distances to our neighbors, like the moon, the sun, and then from there, the planets, the nearby stars, then distant stars, and so on. Distances to galaxies, and so on. So if you didn't know the distance to the sun and the moon, you would get stuck at step number 1, right? So eclipses help kickstart astronomy by revealing those steps in the first few rungs of the cosmic distance ladder. And they also illuminated our path in the pursuit of understanding gravity. Number 1, gave a confirmation of Newtonian theory, right? Halley's eclipse, and then the comet, and the discovery of the planet Uranus. They showed that Newtonian theory was incomplete. And because during the solar eclipse, they were not able to find Vulcan. So that tells you that the orbit of Mercury needed a new theory, and that was only possible during a solar eclipse, right? And Einstein came up with that new theory, and it was confirmed again by the famous solar eclipse of 1990. So that shows how solar eclipses played an instrumental role in our understanding of gravity. So these are some references for the information I shared and the pictures that I got. So thank you for your attention, and you can get the slides using this QR code.